determine the behavior of the function in the vicinity of its non-permissible value. Okay, I've factored this. X squared minus 9 is the difference of squares, so it splits down into x plus 3, x minus 3, and then it's all over x minus 3. And this is not going to produce an asymptote, and you'll see why in a moment. If we make a table of values for this, I'm going to throw some numbers at this thing, and let's see how it responds. If x is minus 3, for example, here we're going to get negative 3 plus 3. Here we get negative 3 minus 3, and negative 3 minus 3. And that cleans up to, well, 0 times anything is 0 divided by anything is 0. Easy enough. Let's try another one. If x is negative 2, negative 2 plus 3, negative 2 minus 3, and same thing down here. These cancel, we get 1. If x is negative 1, negative 1 plus 3, negative 1 minus 3, negative 1 minus 3. These cancel again, and so our result is 2. These seem to cancel over and over. Is this thing just the value of our expression? Can we just use x plus 3? Kind of seems like it. Let's try a few more. If x is 0, 0 plus 3, 0 minus 3, 0 minus 3. These cancel. Yeah, it seems kind of pointless to track these, doesn't it? They keep spitting out the same value, and so this thing is really what's driving the expression. You can see how people would just scratch out these x minus 3's and say this thing behaves like x plus 3 because it seems to be calling all the shots. This part says 3. These two say something that always cancels out, and so really this is the only part of the expression you need to look at. And yet I'm still doing examples, so there must be, the other shoe must be about to drop. Let's find out. 1 plus 3 is 4. 1 minus 3 is negative 2. 1 minus 3 is negative 2. These cancel, we get 4. Okay. When is something different going to happen? Do you see? 2 minus 3 is negative 1. 2 minus 3 is negative 1. We get 5. Yeah, this is getting pretty predictable. It seems like there's no point to having these things here. But wait, here it is. If x is 3, we get 3 plus 3, 3 minus 3, 3 minus 3. Why is this different? It's different because we can't cancel these. 0 over 0 doesn't equal 1, it equals undefined, and the fact that this is here blows up the whole expression. It's actually undefined for x equals 3. These two things have been canceling each other perfectly everywhere except right at 3, where they produce a 0 over 0 problem and they wreck the whole expression. Now if we keep going beyond that, I'll speed this up because I'm sure you're getting the idea. If x is 4, we get 4 plus 3 is 7, 4 minus 3 is 1, 4 minus 3 is 1. These cancel and we get 7 again. If x is 5, 5 plus 3 is 8, 5 minus 3, 5 minus 3. These cancel, we get 8. Now it's back. This part is driving the expression again, and these are irrelevant again. So with this one, because we have these factors that are canceling out, it turns out, yeah, we could ignore them. Everywhere except right at the non-permissible value. At that point, we get 0 over 0, which is not canceling out, and we get a little blip where the function's undefined. So we have to watch that. You can't just scratch these out and forget they exist. You can put a line through them and say, these are not going to matter except in one spot where they're going to matter a whole lot because they're going to disable the entire expression. Now, what does that look like on a graph? We've been doing curve sketching, and we want to know how this behavior translates to a graph. So let's plot some points and find out. We had negative 3, 0. We had negative 2, 1. Negative 1, 2. 0, 3. This is nice and orderly so far. 1 and 4, 2 and 5. It seems like there should have been a 6 here, and in fact, when we did this point, when we put in x equals 3, we actually got 3 plus 3 equals 6. This part's trying. It knows it's supposed to be 6, and it's saying we should do 6 now. It's only these pieces that screw it up. So this section is saying, I vote we should be the point 3 comma 6, and they're saying, nope, let's be infinity instead. So the function blips there, and then it snaps right back into line, and we get 4, 7, and 5, 8. So this graph, sorry, it picked up a bit of a curve, but that's the idea, is a nice straight line everywhere except right at that point. It behaves exactly like y equals x plus 3, except right there. Now this is not asymptotic behavior. This, when you have just a little blip, one break in your line, is called a point discontinuity. So you can say this function is point discontinuous, or it has a point discontinuity, and we can ask you even where that point is. Where is the one little blip where the function seems like it should be, but it disappears? And the way you find it is just cross out these factors and say, if these weren't here, how would the function behave? It would behave like x plus 3, which means it would be 3 plus 3 equals 6. So the point 3 comma 6 is not in our function, but we can say it's the location of the discontinuity. It's the place where there's a skip in our function. So when you see division by x minus 3, the first thing you probably think is an asymptote, but you do have to analyze it carefully before you make that decision. Here, you see an x minus 3 and you think, oh, trouble at 3, and then you see, oh wait, but it's going to cancel. Everywhere except right at 3, these two factors are going to cancel each other out. And at 3, they will just produce this little blip or hiccup or point discontinuity.